the fluctuation dynamo is the generation of the random magnetic field by a random flow. Generally, turbulence isn't needed. To have magnetic field growing, you only need a randomness or large chaos. But in reality, most, if not all, random flows are turbulent flows. Therefore, we will consider dynamo in turbulent flows where there is a reasonably well defined and developed inertial range spectrum, power law spectrum. And there are good reasons to believe that the properties of the solution will depend on the slope of the spectrum. But all the numerical simulations available, they have little control on the spectral slope. You have your driven turbulence, and then the slope will be whatever the Navier-Stokes equation will decide to make. Therefore, it was always difficult to have this additional test of the theory, to see if our expectations, how the results will change with S, with this spectral slope, whether these expectations are confirmed or not. And I will suggest a model fluctuation dynamo which allows you to address this question. But then, when you start talking about the scales of a random field, we're almost talking about the sizes, scales of the either surfaces, for example, of B squared, of magnetic field squared. And then you need, especially for random fields of that complexity, you need objective quantifiers of morphology, which, what, I'm shouting not loudly enough.
For the camera.
Oh, okay. Then we have to be sure that we talk about the same things, that two people who look at the same colorful picture, or maybe a sequence of pictures arranged to what people call a movie, that two different people see the same thing. It's not always the case. And very often the arguments arise just because different people see different things in the same picture. Instead of pictures, I would prefer numbers. Like, well, we were taught by people started from time of Gauss, right? That if you want to analyze the data, reduce them from pictures to numbers. I will try to reduce morphology, complicated morphology of a random field, of random solution, to numbers. And then the final conclusion will be the following. We were able to identify three length scales in the magnetic structures produced by the fluctuation dynamo. We argue that they have the shape of magnetic filaments whose thickness depends on the spectral slope. It's basically 3/4 in Kolmogorov spectrum 5/3, whose width behaves differently. It shows the scaling on magnetic Reynolds number Rm independent of the spectral slope. It's a distinct behavior. It's a distinct behavior. This 0.555 is the slope determined numerically. Most probably just 0.5, 1/2, but impossible to say. And the length of the structures is independent of Reynolds number. It's just the correlation length of your random flow. But let's now move step by step. I would appreciate interrupting, if you will be interrupting me with your questions as soon as they arise. So don't be too shy. If you have a question, just shout this question out. So, if I have a random flow, the only condition I need for it to produce the dynamo is that the magnetic Reynolds number is large enough. Depending on the value of magnetic Planck number, the critical value of Rm is either something of the order of 50, between 30 and 100, and it apparently grows slightly, not slightly, maybe strongly, for small magnetic Planck numbers. What is remarkable about the small-scale dynamo, that it produces magnetic fields which are strongly non-Gaussian, intermediate. They are concentrated with what is variously described as filaments, sheets, ribbons. The vocabulary here is quite broad. The magnetic field within these filaments is presumably similar to the equipartition with kinetic energy density. And they have relatively low volume field factor. So B squared average is significantly smaller than the kinetic energy by factor of sort of 10 for modest magnetic Reynolds numbers. And the kinematic stage of this process is fairly well understood. These magnetic structures have their skin depth, thickness, they're very thin, but nonlinear state is, as it often happens in dynamo theory, is understood much worse. And there is a controversy. The two dominant viewpoints now are the one which is suggested by Alex Shikochikhin and his co-authors, who say that in the steady state, magnetic field has the shape of folds, where magnetic lines behave like this. I'm exaggerating slightly this picture, and this thickness is very small, Rn to the power minus 1/2, and this length is of the order of 1, of the energy range scale. The other model suggested by Candace or Romanian is that what happens in the nonlinear stage is that magnetic Reynolds number is renormalized to its critical value. And the critical value is quite moderate, of the order of 50. And then you have isolated filaments, and magnetic field behaving like this. You have here the magnetic filament whose thickness is Rn critical to the power minus 1/2. This Rn and Rn critical can differ by many orders of magnitude. This is of order of 100. This can be of the order of God knows what. Anything above million or perhaps 10 to the 20th, depends on whom you ask. But anyway, this thickness is very small, and this is quite reasonable, macroscopic anyway. Let's make this estimate. Let's estimate the thickness of magnetic structures in a multi-scale flow. I will start with the induction equation. And I will say that the thickness of the structures is controlled by the balance of stretching and magnetic dissipation, skin layer depth. I immediately get from this that magnetic scale, the scale of magnetic field, times the velocity at this scale should be proportional to that eta, magnetic diffusivity. Now, if I have a power law spectrum for magnetic field, I know how V depends on LB, I immediately get the scale of magnetic field. Thank you. The scale of magnetic field depends on how it depends on the spectral slope. For S equal to 5/3 Kolmogorov spectrum, I get the value 3/4 here, familiar to many. So this is my prediction for the behavior of this width here as a function of Rn. Yes?
That thing that Shikochikhin was talking about, I mean, that was for pickups, sort of scales of arithmetics, large random number, right? Whereas what you're talking about is more, sort of in Kolmogorov range.
Yes, yes. Here, my arguments here apply these ones. For small quantum number, yes. So small magnetic quantum, where everything occurs within the initial range. Yes, true. Within the initial range. But
this Rn for 3/4, then in WQB solutions are created.
yes, it's but again, for prime number it will do one, right?
No, large single scale flow.
Single cell flows, yes, also have it here. Yes, I'm done.
You should replace this guy in minus 1 power. It is just misprint.
Right.
It should be proportional. Okay, what is V square? It is
5/3 means Kolmogorov spectrum.
5/3.
The energy is the integral of V squared decay.
Minus 5/3 plus 1. It gives you minus 2/3. 2/3 is precisely V square.
So V is equal to K to power 1/3 here, right?
Right. But
That's it.
it's not. It doesn't. No. Okay,
It's arithmetic, right?
What's the problem?
So these are examples of magnetic structures obtained in numerical simulations by Niels Haugen and Wolfgang Doble and Axel, and Alex Shikochikhin and Steve Cowley. These are the structures you normally observe in those observations. So, do we see what we expected or do we not? Is the thickness of these structures, obviously there are thin structures here. Are they as thick as expected or are they not? Are these filaments or are these ribbons? I'm not asking you to tell me. because I know that you will be telling different things, different. Of course, people are clever. When looking at these pictures, they spend quite a significant time trying to make sure that their conclusions are as objective as possible. They're not just jumping on the first possible conclusion. But still, it's a painstaking and unreliable process. So what we did, we had our own model of fluctuation dynamo. We took the velocity field, which was described by Andrew Bagley this morning. It's the velocity field which is prescribed in the form of the Fourier series. These phases phi n can be made time dependent. Because of these cross products here, the divergence of this velocity field is identical to 0. So it's incompressible velocity field, and now we'll choose Cn and Dn as to have the energy spectrum of this field as I wish it to be. And we have chosen, for example, this is modified von Karman and somebody else spectrum. So at small case, it's k to the fourth. At large case, it has exponential cutoff, and in the middle, for kn larger than k naught and less than kd, we shall have a power law. Ek will be proportional to minus s. Again, if you do this arithmetic, these two and these two go, k plus 4 and minus 4 go. You have k to the power s. It's an excellent model. It's an excellent model. So I have a velocity field which has zero divergence, which has a fully controllable energy spectrum. The only problem that I see here, it has a very good Lagrangian chaotic properties. The Lagrangian statistics are very similar to what you get in real turbulence. The problem is that we get it not by solving the Navier-Stokes equation, but sort of from thin air. The price to pay is that Reynolds number is not defined in this model. And the best we could find was to define the Reynolds number, like in real flows, from the ratio of the two scales, dissipation scale and the energy range scale. This ratio in real turbulence depends on the Reynolds number. So we define Reynolds number in terms of Reynolds number in quotation marks, right? It's an effective Reynolds number in this problem.
But would you comment, with these random phases, of course, you won't have, correlations like in a real turbulence, for example, for the third correlator. I mean,
yes.
Do you think it matters for
Sergey, I don't know. But on the other hand, if by using this model I will discover that third correlations matter for the fluctuation dynamo, I would be proud to have achieved such a result.
Yeah, can you say fiddle with phi in such a way that to make non-zero third correlation? Just choose statistics, not random phases, but
Right now they are not random. They are just numbers. So here it's not a random flow at all. As we use it, it's not a random flow. We pick Cn and Kn's at random, well, the directions of K's and the directions of C's are picked at random. But since having picked them once, we don't change them in time. So in this sense, the velocity field is not random. It has Lagrangian chaotic properties, but not randomness. But on the other hand, and we haven't done it yet for various reasons, but we shall do that. We can always make it genuinely random. For example, we can update either phases, make them these omega n's random numbers, or even the amplitudes. We can, every now and then, we can rerun our random number generator and have a genuinely random field. So the velocity field is flexible enough to provide this ability. We haven't done it yet. But I agree with you. Here we can start exploring. For example, I can make this velocity field helical. It won't be difficult to make it helical and study the alpha effect here. It's the same thing. So I like this model, even though this is the only disadvantage of this model that I see, that the Reynolds number isn't reasonably defined. Yes,
Tell me please, in frame of this model, is it possible to reproduce Alex Sikachkin structures?
I hope so. Why not?
No.
Let's see.
It's possible.
Hopefully.
Okay, very nice.
But I don't think so, because I mean, his structures appear like that when they high Prandtl number regime, right? Whereas you don't want to consider that, right?
Why not?
How you do it? Yeah.
So this is the spectrum we have. So what we did, we calculated this velocity field on a grid, numerical grid, and then Fourier transformed it, and with 40 modes, so this number m is here. We include a certain number of modes, right, obviously. Well, Louise, if I remember correctly, Louise Wilken, she also had runs with 600 modes, you know, almost continuous spectrum. So here, just 40 modes are included, and you can see how nice is the spectrum. Even with 40 modes, the slope is very close to 5/3. This is the dissipation length. This range corresponds to the Reynolds number of order 16. And the magnetic Reynolds number in this simulation was 2000. Well, Andrea was telling us how his supervisor made him to present additional results in his form. You are lucky people, because I tried to convince Louise that the number, the 2000 is a too higher number for the resolution 228 cube that we had here. But she was fantastically persistent. She was an excellent student. She was very persistent, and she was telling me that there are no signs that we lose resolution. All the results we have look absolutely perfectly nice for Reynolds numbers are up to 2000. And so she persistently was showing these results. I will follow her advice. If she doesn't listen to me, I will listen to her. So, this is the growth rate of magnetic field. Just to, I shaded out though that part, which I personally believe may be not that reliable. But Louise insists, and this is the growth rate of magnetic field of kinematic model as a function of Rn. Indeed, she's right. The curve is perfectly systematic, smooth, behaves nicely. Moreover, the logarithmic approximation, which we borrowed from your paper, works perfectly well. Here, with the accuracy of 96%, I think she should. Just deviation from your asymptotic result is
Strange
next to
for us.
nothing. Next to nothing. So she probably has the point. I don't know why she's right, but she may be right. So it seems that the system works. We do reproduce more or less standard properties of fluctuation dynamos obtained for other flows. And now these are the other surfaces obtained in this one. We published this in Physiograph Letters last autumn. So what do you see here? These are the other surfaces of B squared. Are these filaments? Are these sheets? If I put you to separate rooms, so the same picture, not allowing you to communicate, and then bring you back, will you tell that you have seen the same or not? How results will change if you change the level of isosurfaces? These are 1.5 RMS value isosurfaces, I think. What if you go to the level 3? Obviously, these will be isolated points. They will be like balls, like spheres, at very high level. At a very low level, you see the fold. So when you say that these are filamentary structures, at what level? Is your conclusion robust? Is it reliable? How do you know? The normal answer is I've spent hours looking at colorful pictures like that to make sure that my results are reliable. Excellent. But you have spent those hours in a better way. Minkowski functions. There is a mathematically rigorous diagnostic of morphology. And this is based on Hadwiger's theorem, proved in 1957, who says that the idea of the theorem is the following, that in a space of dimension D, there are 4 independent functionals which are additive and translationally invariant. And any functionals which are translation invariant and additive can be expressed in terms of the D+1 Minkowski functionals. In 3-dimensional space, we have 4 Minkowski functionals. So, in this sense, these 4 Minkowski functionals provide complete morphological and morphological and topological characteristic of the surfaces, random surfaces in 3-dimensional space. What are those functions? The volume. Imagine I have isosurfaces. So I want to know what is the morphology of the regions enclosed by isosurfaces. I will calculate the volume enclosed by isosurfaces. I will calculate the surface area of those surfaces. I will calculate the integral mean curvature. There will be at every point, there will be two curvatures defined, kappa 1 and kappa 2. And then I will calculate the Euler characteristic, something related Euler characteristic, or Gauss's curvature. And that's it. Now the question is, okay, calculating volume is easy. Calculating surface area is hard. How are you going to calculate the curvatures? It can be quite a difficult numerical problem. But by the way, an excellent paper of Varun Sapni and Sergei Shandarin and their co-authors, and this were from I borrowed this method. It was used by people in cosmological structure formation, because they were really worried about the morphology in their models. So fortunately, there are very simple ways to calculate Minkowski functions, again, based on rigorous mathematics. To calculate all these four functions, the only thing you need to do is to calculate the number of grid points, imagine a cubic grid, within your structures, number of complete edges of your grid within the structure, number of complete faces within the structure, total number of grid cubes within your structures, and big N is the total number of grid points in the domain. And then it can be proved that the four functions can be expressed in terms of these, 5 numbers, which can be always applied by simply counting grid points within your structures. These two papers discuss it in detail. They don't provide all the proofs, but if you send an email to Louise Wilken, Google will help you to find her email. Her thesis contains all the proofs in very fine detail. And then, so calculating this Minkowski functions is easy and straightforward. We shouldn't be worried about this. We can always do that. And then, but still, all these quantities have different dimensions. It is convenient to have dimensionless measures of morphology. And this is what people do. It is, again, we borrowed it from previous papers of both Varun Sapni and Sergei Shandarin. You introduce thickness, width, and length. Don't ask me why you have 2 over pi and so on. This formula I adjusted just to have reasonable results for spheres and cubes for simple bodies like that. Then, dividing by volume, by surface area, you get something which is, you can call thickness. Volume divided by mean curvature gives you something which can be identified with width, and likewise length. And then you can introduce by combining width minus thickness divided by their sum. This is what it's called, can be called planarity. If you have a perfect pancake, it will have planarity 1, and filamentarity, which is length minus width, 0. A filament will have planarity 0 and filamentarity 1. Sphere will have both equal to 0. So, again, this was the idea of Varun Sapni and Sergei Shandarin. A few examples here. This is a perfect sphere. It has, so what Louise did, she had in ideal these volumes, and she calculated Minkowski functions for these spheres on the grid she had. So for this sphere, both planarity and filamentarity are close to 0. E is a filament with an elliptical cross-section. Planarity relatively small, filamentarity is larger. D, another filament. D. Planarity is small, filamentarity is larger. So you see a diagnostic from comparing these two dimensionless numbers to get an idea, with some experience. We need some experience to do that. What sort of structures you have. And then, but still, if the surfaces are concave, sometimes this T, W, and L are not arranged that T is smaller than W is smaller than L. Therefore, in what will follow, we always choose L1 as the minimum of the 3 thickness, the average, of the mean of the 3, the median, what was in the middle between those, we called L2 width, and the largest dimension was called length. Thickness is a function of Rm.
What about more kind of traditional way to just measure moments?
I will come to this.
So that's where you can derive what kind of structure is dominant based on moments. So you can as well just measure moments. Right?
But in reality, moments are difficult to calculate, right? Here, to calculate all these variables, I just integrate. I just integrate within my volume, and that's it. It's just one simple operation. which doesn't, no differentiation is involved.
Just
To have higher moments, I always need good statistics. Moreover, it can be proved that Minkowski functions contain information about all statistical moments, not just the first, second, the third, and how it depends on how much enthusiasm you will have. It contains information about all statistical moments simultaneously. So why should you lose information if you can retain it in such a simple way, by just adding numbers of vertices and faces? Instead, it's always a pain. Calculating higher order moments is always a pain, right? Even in laboratory experiments. Now, imagine these observations with, I shouldn't say poor resolution when Ryan and Brian are here, and Marat. Excellent resolution, but still very limited data.
In like a fourth moment, it's not really hard to calculate.
But you have all the moments in one go.
But what's interesting, there is a pretty, analytical solution, like this Gauss spectrum for the second moment. There are also soluble scalings for moments.
Yeah. What you're going to do in isotropic fields? What you're going to do with the filaments? Like this?
No. The filaments is the signature of intermittency. I mean, you see the.
What you're going to do? How many moments you know? But I do know that my distributions are intermittent. I do know it from the beginning, strongly intermittent. As you could see here, how many moments you need to describe this distribution? How many moments? 6, 7, 10? 1, 2. This has all the moments put together. And these are statistically unbiased estimators of this. By the way, this formulae provide statistically unbiased estimates of all this. So it's perfect, absolutely perfect tool. And it's easy to apply. Yes, I must finish. So, thickness, yes.
Trying to understand how 4 numbers can characterize all moments of a general distribution, where there could be more parameters than.
Imagine I have an Navier-Stokes equation, right?
Yeah.
I can always expand it into the chain, infinite chain of moment equations, right? And then you will struggle solving this moment equation, first 10 of them. But then I will leave the room, come back to the exact solution, and bring you the exact solution on one piece of paper. It will contain information about all your movements, right? But will be one single, perhaps very simple solution. Why not? Why not?
So these are 4 numbers,
4 numbers.
as a function of scale or something like that?
You can change the level.
Level of?
The level of isocontours. Then you will be sensitive to the spectrum, I think. Right? Yes, Austin.
So I can easily see how this is well suited in order to compare different simulations with each other in order to see if they agree or not. But what happens to your Minkowski functionals if you add noise? So then your surface,
Yes, there is some problem here, which will be discovered with Rodeo just last week. Because since they are sensitive to the curvature, this means that by smoothing the data, you can affect your functions very significantly. Because the curvature will be changed. True, true. But give us some time. Give us some time. At least when comparing numerical simulations, they're a perfect tool. How useful they can be when applying to real data, it's a different question, which I'm not prepared to answer as yet.
Yeah, which is even worse that most of the real data is a projection, so you have only 2D information.
But this is okay. No. Here, projection means less noise. In this sense, it's better.
Oh, well,
But what I would say that since there is no magic in nature, right? If this fail, most probably all other methods, or most other methods, will also have severe difficulties for the same reasons. Because now, from this experience, we see that the conclusion whether what you have is a filament or a ribbon depends on whether you resolve it well or not. Right? This difficulty remains whatever tool you use. So, this is the behavior of L1 thickness as a function of Rn. This is the expected power law behavior, this minus tau s plus 1. Perfect agreement for s equal to 5/3, 2, 3, confirmed as well as we could. I will not go to details. L2 width, similarly, and L3 remains constant independently of Rn. Quite a nice agreement. Now, we also tried what one would call an integral scale, right? This is what usually people measure. The scaling is 0.42. for all S, it's independent of S. O42 isn't physically meaningful number, not surprising. You have structures like this. You want to characterize them with one scale. Of course, this O42 is the mixture of 3 quarters, all 55 and 1. It's like the average temperature of patients in a hospital. It's 76.6, but some are dying because of fever, the others dying or already in the cellar. It's a single mixture of all those scales. We also tried other scales, scale measures proposed in various papers, no, in Alex Chikachikin's paper. They show no meaningful scaling with RM, unlike the measures obtained from Minkowski functions. And finally, we also now we can check how this fragmentarity and planarity depend on RM, and we see clear evidence that as RM increases, fragmentarity becomes larger than planarity. Progressively, the magnetic structures become filaments. These are our asymptotic behaviors for fitted, of course, just fitted, for large RM. Remarkably, current is concentrated on ribbons. For large RM, you have ribbons. The planarity and fragmentarity are both large. So magnetic field is on filaments, and current is on ribbons. Not surprising. Current envelopes the magnetic filaments, so it's a ribbon. And finally, what other measures can it do? You can check how stable ion results depending on the level of your isosurfaces. So you can easily now have a isosurface at arbitrary levels alpha from 0 to 14 RMS values. You calculate your measures just to choose the range where they're reasonably stable and consistent. And you get from 2 to 5. Not surprising. This is exactly the range where clever people like Alex Chikotchikhin or Axel or other people work. But now you know why it is. You know where it is. You can measure this working range for either surfaces where the results are representative and stable. Thank you. Sorry for being so slow.
Questions?
You have these Minkowski functionals for isosurfaces of the magnitude of B. So it will tell you something about the topology of these surfaces. Is it clear that it will give you something about the geometry of the vector field B?
Probably not. Probably not. These are just isosurfaces. Just isosurfaces of a scalar function.
Is there something comparable to these Minkowski things for the vector field?
Not to my knowledge. But I think that in such cases, vector wavelets, where Rodeo or Peter Fried are experts, would be perhaps a better tool. Then just maybe it's better to expand it over a certain basis, say wavelet basis. Then you can combine this to study the scalar aspects of your problem. Well, for example, they are not good for anisotropic distributions. One thing is to say that everything is in filament, but this filament can be either isotropically distributed or all aligned. This stuff will not tell you which of the two you have.
You know, I think I have related to what you just said. I mean, so you kind of measure structure by structure, right? So like these pancakes, for example, right, or ribbons. But I mean, if they are folded, I mean, these structures tend to get organized into the layer. You know, so they're correlated one with another, right?
Yes.
And in some sense, you know, Fourier space might be even more appropriate for them. Because if you have something layered or exhibiting some sort of periodicity, you can look at structure in Fourier space, instantaneous realization. So they would correspond to kind of needles, very long sort of ellipsoids like that, and your minimal thickness would be just cut off somewhere at the resistive scale, you know, of your needle, you know, in Fourier space, right? So you can have this spiky structure like porcupine, you know, in Fourier space.
Or if you just look at correlation function, if it's a folded structure, we discussed it with Andrea another day, then you will have autocorrelation function be oscillatory. It will be positive correlation at this distance, negative at the next distance, and so on, something like that. For unfolded structures, it will be more or less normal autocorrelation function. So for those purposes, normal correlation analysis or spectral analysis is better. But there's a broad range of questions which people persistently discuss as important questions, which can be best addressed with this tool. And the tool is simple. The tool is fantastically simple. Not using it is a shame, just wasting an opportunity.
critical magnetic resonance number which you presented here.
700.
Yeah, it's
53.
about 700. Yeah.
753,
So
yes.
as follows from our theory, based on the delta correcting time, based on the correcting Kazantsev model for velocity field of delta correcting time velocity field, the threshold of the order of 400. Yeah, numerical simulation by Alex Shikachikhin and company showed that the critical magnetic resonance number of the order of 200 or 250. What do you think? What is the reason such
It's
frequencies?
dirty business. Igor, it's dirty business. First 2 pi is hidden here.
Oh, okay.
We don't have 2 pi. So first divide everything by 2 pi. But that's somehow the principle of purity of science. I insisted that this 2 pi must be there. So 2 pi is included here.
Okay, I
right?
understand.
So first divide 700 by 2 pi, you go down to 100. Second, it's the flow which only has Lagrangian chaos. It's not a genuine random flow. Of course, it doesn't have the time.
Do
Right?
you attribute this change of slope is like this sort of anomalous, dissipative anomalies, or you kind of you go into the like in Kazakhstan Krashen dynamo, or is it just accidental?
What?
Well, like in Kazakhstan Krashen dynamo, right? So you have first non-dissipative exponent, right, and then you get you switch to another regime with lesser.
But you just one asymptotic logarithmic behavior with Rn.
Yeah, this is important.
Just one single asymptotic logarithmic
Yeah.
logarithmic branch.
Yeah, but could I continue the question? Yeah, and in principle, by this procedure, is it possible to study the case of large magnetic quantum number or not?
Small, you mean?
No.
You know what?
He studied
What you want?
magnetic quantum
Do you
number.
want the answer I would enjoy giving, or you want truth?
Both.
Both.
This is large
If both, the answer is yes. If truth, I don't know.
Okay.
large magnetic transfer.
No.
Effective
Yeah.
How you can define quantum number if your Reynolds number is poorly defined?
Okay.
Yeah, but your flow is cut off and the magnetic field grows on smaller scale.
This means, what you are saying means that my Reynolds number can be meaningfully defined that way. Perhaps, or maybe not. I simply don't know.
Yeah. Okay.
Maybe we shall be able to clarify this and convince ourselves that this definition does make sense. Then I will come to you again and say my dishonest answer was correct.
Yes.
But otherwise, I will withdraw and say I'm sorry. I don't know.
I have a question exactly about this definitional. It looks like something wrong. If you take the slope s equal minus 5/3.
Plus 5/3. I have minus here. I have minus here. So take plus 5/3, we'll have 3/4. I checked it when preparing the talk. This I checked. Because I keep confused myself with these minus and pluses. As positive as negative. Yeah, and this I checked.
Yes, I can understand it working well in three-dimensional data, but if you think about two-dimensional data space, and if my field is, for instance, some kind of emissivity, so I have to impose a threshold, and in this case, if I have overlapping structures, won't I mix different topologies, for instance?
For example, you can have something like that, right? This will be a filament, and this will be sort of a two-dimensional sphere. In two-dimensional space, there will be 3 Minkowski functions. Okay, fine, you will have a mixture. Then you can, if you have good reasons, you will divide the region into 2. You will see that you have a filament here, and you have something isotropic here. So in this sense, it's okay. And with Rodion, we applied Minkowski functions to intensity data, exactly that, just last week. And the problem we encountered was that, in fact, with high resolutions, you will have this. If you smooth the data, you will get rid of this, but the curvature here is important. And the Minkowski functions depend on curvature. So this, maybe we shall get away with that. Maybe we shall find a way how we can still make sense from the smooth data. But right now, I don't know how to use it. Because of the smoothing. If you have perfect resolution, or resolution you think is satisfactory, then go ahead. Then there will be no problem.
So last question.
It's not a question, it's a comment. Let me say a small comment about why its stupid formula is more or less good. It means just that Kazantsev's theory is very good. Nothing.
Wait a minute, which of those formulas you think is
I mean, you say that it's strange that it's true. It's because it
what?
Well,
This logarithm.
Yes.
It's not strange, I'm just happy.
The reason is that the Kazantsev theory, very close, delta correlated Kreisel-Kazantsev theory, very close to reality.
But surprising, here the correlation time is infinitely low.
Yeah, but
this is not a random velocity.
Correlation time doesn't matter at all.
Yes, it's a Lagrangian chaotic system.
Exactly. So because all that matters is the finite Lyapunov exponent.
Yep.
And it's not even a statistical result. So
a couple of words. And what's interesting, this sinus logarithm solution, it is exact solution practically for any spectrum of turbulence if we're close to threshold of generation. It's mathematical fact which proved maybe a couple months ago, maybe half year.
Okay, we finish here. Last speaker is Dandu from my end.
Right. So when we organized this program, we thought that all the organizers should come last. And I was telling Anwar, then there was a thought about putting us all alphabetically. Of course, it all changed because we didn't turn up. And then I was telling Anwar that, hey, whatever you say, I'm going to contradict that. And I will have the last word. But it turns out that Igor will have the last word, and he's already written it all here. So I will not contradict what Anwar says. So I'm going to talk about helicity, magnetic helicity, which already Ethan has given you some thoughts on, and I'm just going to give you some further thoughts. Also, what has happened is many of the things which I've been doing has been done by Sharanya. So once Sharanya has given his talk, I have actually nothing much to say, which is more recent. But I have some new thoughts maybe which I will share. So I'll talk about helicity and its flux. So this is the plan that I want to put everything in the context of the mean field galactic dynamo. You have already heard about the stellar dynamo part. So I just thought I will change it slightly. And what is magnetic helicity? And there may be a lot of people in the audience, especially the younger generation, who have not heard any of these things. And so maybe worth looking, just saying something about that. And then helicity, evolution, and conservation. Then I will, of course, people don't believe alpha exists to quench, but if it did exist, then it can get quenched.
Don't believe that alpha exists, don't believe that it's quenched.
Yes. And then I'm going to try to motivate and push a way of looking at helicity, which is probably not familiar to most of you, because even if you have heard of helicity, you would always hear of A dot B. And I think this is not the right way to look at it. And that will allow me to think a little bit about what is helicity, density, and flux. Although everybody has talked about this, I've always been a little uncomfortable, and I'm just going to do that, and then we'll come to conclusions and questions. But to begin with, to set the scene, this is the equation that we all are looking at, the induction equation in some average form. So you have some stochastic forcing, and you're looking at various statistical moments, and this is the first moment. We just take the moment of the magnetic field, is the average magnetic field. You're on top of the induction term and the resistive term, you get a new term, which we all call the turbulent electromotive force, which is small u cross small b average, small u and small b being the stochastic or the random velocity and magnetic fields. And it's a way to determine what this is in terms of the mean field itself. And if you could do this, then you have a closed set of equations which you would love to solve. And this is a standard closure problem, even in the kinematic stage. And the idea which people have always had, at least in the case when things are isotropic and homogeneous kind of turbulent situation, is that once you do an expansion in powers of derivatives of B, and the first term you get is something proportional to B, the next term you get is something proportional to curl of B. The curl of B would just add to the microscopic diffusion called the turbulent diffusion. And the thing which is proportional to B is what we have all been arguing about, the alpha effect. In the galactic context, the galactic shear which is given to you, and which is something which you cannot do much about because it's governed by gravity, which has nothing much to do with all the turbulence that's going on, is given to you, and that generates from any radial type of fields. And I'll borrow a figure from Anwar's and Dmitry Sokolov and Maikin's book. Any radial field gets wound up and you get toroidal fields, and the alpha effect, the crucial thing it's required, is to regenerate the poloidal kind of fields by twisting this, by creating loops of the toroidal field, twisting it appropriately, letting them all merge, and then trying to then regenerate the radial field. So this is what the alpha effect does for you, right? In the galactic context, it's a supernovae which drive the turbulence, and because you have a rotating, stratified kind of system, the turbulence becomes helical, and these helical motions generate dr from d5 and lead to an exponential growth of the mean field, if you believe all this, on time scales. Now I've added, after the discussion of Reiner and Wahr, 10 to the 8 years to 10 to the 9 years. So I have changed now after 20 years. Right. Now, so there are certain problems associated with it. There are several problems. There are all problems. Russell Kurzweil keeps emphasizing this problem of getting rid of the wrong sign of the flux from this disk. And that's the ejection of flux. I'm not going to talk much about that. People have raised the problem of having generated these poloidal fields, you have created links between the toroidal and poloidal fields. So you have created what I will soon refer to as a helicity of the mean field. And how did you do this? By conserving helicity. And people have also talked about the problem of, if you generate all this noise, then what do you do to the Lagrangian chaos of the system? And of course, even the kinematic state is all these things working around. But I'm going to just concentrate today on the helicity question. So magnetic helicity, and I'm going to follow for now, for the next 5 minutes, the standard definition is an integral of MHD, an ideal invariant, and it's given by A dot B, where A is the vector potential, curl of A is the magnetic field, and integrated over all volume. Basically, because you're using the vector potential, it's a gauge-dependent quantity unless the field satisfies certain restrictions, that it either vanishes on the boundary or it's bounded, so that when you're integrating to infinity, if you make a gauge transformation, if you add a gradient to the vector potential, which will leave the field invariant, it can change this helicity. So you need a closed volume in some sense. It measures the links in the field. Twists are also actually links in some sense, because if you take a bundle of field lines, you could concentrate on one field line and see how it kind of rides around the place. And you could also concentrate on neighboring field lines and see how this is linked to this fiducial field line. So one is called the twist, the other is called the ride, and it measures this quantity, which I won't show you exactly. It's found in the standard textbook, for example. And this is just an example pulled out from Berger's Mathematica things, which he puts on his webpage, and they are very pretty pictures, always pink in color for some reason. And the helicity evolution is different from the energy evolution. The magnetic energy dissipates in where the currents are large. The helicity can be both positive and negative, can get generated or destroyed, where J dot B is large. Okay? And in many contexts, it turns out that even when energy is dissipated at the rate at which you put in the energy, either due to viscosity or due to resistive loss, the helicity does not evolve as rapidly as the energy. And so it can be nearly conserved even when energy is dissipated. Of course, as there was this discussion between David and Ethan, and also as Axel clarified, there can always be eigenfunctions where the helicity is changing, okay, with time, or growing exponentially or decaying exponentially. But because of this eta factor, unless the eigenfunction is biased towards very small scales, you will not generate the net helicity as rapidly as you could generate the net energy. Now, given this, that the helicity is roughly conserved, how does the galactic mean field helicity, which is reflected in these pictures, for example, in these links that you have between the toroidal and colloidal field, how does it arise? And the answer is fairly well known now, that you should not think about one field line, and this is a picture due to Eric Blackman. Also quite confusing. Yes?
I didn't find in your previous slide flux of helicity.
Not yet, because I'm integrating over all volume.
All volume.
Yes, the whole universe.
You are really lucky if you can do it.
I'll come back to your flux, yes. I'll come back to that. So you should not think about single field lines and twisting them, but the idea is that you should think about a bunch of field lines. And whenever you do think about a bunch of field lines and you try to write them, take a bunch, make a loop and try to twist that, you also automatically conserve helicity because you are not doing any dissipative thing here. Okay, it's an ideal invariant. But the right helicity and the twist helicity that you produce turn out to be equal and opposite so that you still conserve helicity. And this is what happens in the alpha effect. The turbulent EMF transfers helicity. It puts oppositely signed helicity in the large scale right of this mean field and the twist of the small scale structures inside there. And you can do this mathematically. The only thing which I want to just point out is that as you grow the field, these twists, which are on a smaller scale, okay, for a given helicity, they will exert a larger force and they can want to untwist. And so you will get a back reaction due to the twist that you're going to create all the time. And they can come and try to cancel your alpha in the sense that your kinematic alpha, if it wants to take loops and twist them, but the twists that you're keeping on introducing are trying to untwist these things. So that can be a nonlinear back reaction. If you want to go and look at it more mathematically, then what happens is that if you look at the Ohm's law for the mean magnetic field, then the Ohm's law is, J by sigma is E plus U cross B, but now you have an extra turbulent EMF. And the helicity evolution, which is d by dt of average A dot B, which is going as E bar dot B bar, gets an extra piece due to the turbulent EMF. And if you subtract from the total helicity equation this equation, then you get the equations for the mean magnetic field and the equations for the, mean helicity and the equation for the small scale helicity averaged over some scale has equal and opposite sources, sign sources, and it's this turbulent EMF, or more precisely the component of the turbulent EMF parallel to the mean magnetic field, which transfers helicity between scales. So this is something where you are getting scale separation in helicity, something which was actually invented, realized long time back by our chairman here in his early papers. But there is a problem here that if you ever go to a stationary state and d by dt of small a dot b goes to 0, then this parallel component can go very small as the resistive kind of limit, and so as eta, the resistivity, goes to 0, you can get a catastrophic quenching of E parallel. And the way out of this problem has been suggested by a number of people, starting from Blackman and Field, even before Kleonin, Dobzhevsky, and other people here, Ethan, Joe, and the basic suggestion is that you need helicity fluxes, or fluxes of small-scale helicity in the system, so that you can sort out this problem. One of the questions which I was always puzzled by, and that's what I'm going to talk about, is how do you talk about a flux of helicity, where I told you that helicity is a topological quantity which measures linkages and measures something which is non-local at some extent. So what do you mean by, firstly, a density of helicity, and what do you mean by a flux of helicity, density? So this is something which we worried about, and at the end of this famous Newton Institute program which Axel was mentioning, we came up with a kind of definition. And this definition was kind of motivated by taking a step back. People have brainwashed you by saying that helicity is A dot B. And actually helicity is not A dot B, it's measuring the linkages of the fields. So you should go back and ask what measures linkages of fields. And actually it's the Gauss's formula which measures linkages of curves. So if you take a magnetic field as a set of all small flux tubes, okay, and these are kind of fiducial curves, then it is Gauss's linking formula, which is a definition of actually if you have a magnetic field B at x, position x, B at position y, then if you calculate this double integral over volume, this measures all the linkages in the field. Of course, if you want to think in terms of the vector potential, then what you recognize is that one part of this is nothing but the vector potential in the Coulomb gauge. That is, if you define curl of A to be B and divergence of A to be 0, this is something which you're used to in the Biot-Savart's law when you're talking about curl of B being J and divergence of B being 0. You know that you can write the magnetic field in terms of the current density exactly in this form, and if you plug this in, it is A dot B. But this only means that your A is purely the Coulomb gauge A. So the more basic definition of helicity, which I want to emphasize and push, is what you get from the Gauss's linking formula. Now, does this allow you to define a density of helicity? It allows you to define a density of helicity only in the case where you have a random field, and in this random field, you have a correlation scale which is smaller than the scale of the system over which everything is varying. So suppose you have scale separation, you have a correlation scale L, you have a scale of the system Rs, and you have some intermediate scale which is well separated by these two, from these two guys, which is an idealization, of course. Then it is possible to measure, to define for yourself a density of helicity which varies from point to point. And that you can do by taking, for example, the ensemble average of this. That will lead you to this expression. This is exactly the same as this, averaged over, let's say, the random field small b. What you get b dot b will become, b dot all this stuff will become the magnetic correlation function. And if you do not have a homogeneous system, if you have an inhomogeneous system, this correlation function can be changing from place to place in a slow manner. This is the kind of systems that we are considering, that there are two scales in the problem. A scale over which the small scale field is changing rapidly, and a scale over which the average properties of the small scale field are changing slowly with space. This double integral over d cubed x, d cubed y can be written as an integral over the separation between x and y, and that's mean position of x and y. And then this integral over just the separation converges even if you integrate over an intermediate scale, L, because the correlation scale is much smaller than this intermediate scale. So you can identify this piece as the density of helicity. So the physical idea is that you're looking at, suppose you stand at a place and you look at all the links around you, then very far beyond the correlation scale, there are no longer links which are correlated with you, with the magnetic field here. So within a correlation scale, you count all the links, okay? Divide by the volume that you have used, that will give you a density of links. Go somewhere else. Again, count all the links within the correlation scale, that will give you a different number. So this density of correlated links can vary with space. And this is the idea that you can exploit to at least define for yourself a gauge invariant density of helicity. And now we have a density of helicity. You can ask what is the evolution equation for that. And that evolution equation, of course, gives you more or less what people have all been expecting, which is a flux equation, a local helicity conservation equation. So most of the kind of conservation equation you may see will all be integrals over large volumes. Here there are no integrals over large volumes. Of course, there is still the averaging going on. So this is an equation which says that the helicity density, rate of change of helicity density, is governed by the sources which we had before, the turbulent EMF and the dissipation, but also has a divergence of a flux. That flux you can calculate now because you know exactly what it is. Other people have calculated even without wanting to clarify this point, and this is my personal taste to some extent. So that flux has various pieces here. But the importance of that flux is that now if you go to the stationary limit, if you put dH by dt going to 0, then the turbulent EMF need not just be balanced by the resistive dissipation, in which case it can get catastrophically quenched, but it has in principle can get a balance with the divergence of this flux. And this is what Ethan also talked about, that if you have a helicity flux, then you can drive your dynamo through this helicity flux. Okay, so that is this part here, that now in the stationary limit, the turbulent EMF, parallel component of the turbulent EMF, is no longer just this term here, there should be a 4 pi by c here, but there can also be a divergence of flux. And so you hope that there is no catastrophic quenching in the presence of this flux. Let me go and look at the pieces in this flux a little more. There are two pieces which I have nominally identified with Vishniak and Cho and Kliorin et al. Basically because Kliorin and Grobczewski always worried about something which was anti-symmetric, the alpha effect leading to a flux, and that's why I've called this that. That flux can also arise from here, and Ethan's flux can be actually derived completely from here. Now these two fluxes I'll come to later, depend at this level on the cross correlation between the velocity and the magnetic field. I've not yet simplified this part. And in some sense they are very similar to the EMF itself, which is also a cross correlation with a different combination of the velocity and the magnetic field. There's also another flux term here which I've called the bulk flux. And this is something which Anwar was trying to tell me from day one. And I really like the fact that when you talk to Anwar and Dimitri, they think in completely simple terms. And so after all the complicated stuff, you get exactly this, that there is a transport of the helicity by just a mean velocity field. So you just take all the magnetic field and go somewhere else and you're transporting helicity like that. Okay? So that is the bulk flux. And there's a flux which is a plane, of course, which is a triple correlation. So it has got 3 small scale quantities average. And this is something which will definitely require a closure theory to evaluate. And one doesn't know what it will do, but it comes inside the divergence. So it's not, earlier Axel and I tried to look at the helicity evolution equation through evolution of J naught B, and there we had all these triple correlations in the volume term. And that is something which we do not know what to do with here. But at least in this case, it doesn't come, it comes within the divergence. Now, I want to make a remark which is slightly negative, but it just made with positive intentions. Anwar will like this, but other people may not like. That if the bulk flux was 0, okay, if there was no bulk flux at all, this piece, the EMF, these two pieces, all depend upon this chi in various combinations, which are all UB cross correlations. So you may imagine a situation where you suppress all these guys. You suppress the EMF, parallel component of the EMF, and you suppress these two fluxes catastrophically, and they are all equal to this eta term. So to me it is not yet absolutely clear that you can get a large flux due to these terms if the bulk contribution is 0. It may be possible, but I am not yet completely sure about this. Okay. Now, so let me first, before coming to those two fluxes, yes, thanks, tell you a little bit about the results with at least the bulk flux. Okay, then what we do, we do something which as a kid you are supposed to do. You have learned an essay about the cow. And somebody says, no, write an essay about the tree. Okay? Then you say, okay, I had a cow, this cow was tied to the tree. The cow which was tied to the tree was eating grass. The cow which was tied to the tree is doing this. So you write all your essay about the cow. So this is what I'm going to do now. Okay? So far I have not made any assumptions about any closure assumptions. Now you have to, if you want to make progress in some way, you have to make some assumption. And so what we will do now in the next few minutes is to look at models where we solve the dynamo equation together with this equation for helicity conservation, assuming that the helicity, magnetic helicity, can be related to the current helicity, and then there is a correction to the alpha effect due to the current helicity. This is the Bouquet, Leora, Frisch original result. Okay? Now, if you do that without the flux, of course, then you get back catastrophic quenching. And these are things which is there in a paper with Anwar, Dimitri, Axel, myself. So what is shown here is the mean field. Cu equal to 0 means no flux. Cu equal to something, this is just the advective flux. What we are imagining is that the galaxy has got all these supernova remnants, it has got hot gas, this hot gas leaves the disk and advects out some of the helicity. And because of this, whether you have some effect. So if you had none of these advective flux and no fluxes, then what happens is that the mean field grows and then gets quenched catastrophically. But even a very little amount of this advective flux helps you to stabilize this dynamo. But if you have too much advective flux, then you throw away the mean field together with the, because everything, all magnetic field is going to get advected. So not only the small scale field, but also the mean field is getting out all the time. And if you do this too much, then you quench the dynamo again. So this is, these guys which are going down are with large advective fluxes. It turns out that, okay, so you can see more clearly in these eigenfunctions which Axel calculated what's happening. These are the saturated eigenfunctions. They don't look very different from the actual kinematic eigenfunctions. This is what Anwar was probably referring to when he said these things do not change in the nonlinear state very much. But what has happened is that the alpha effect, which in this particular example was taken to be proportional to Z, has got completely quenched in these regions, but has not got quenched because of the flux in these regions, and that's what keeping the dynamo alive. Now, qualitatively similar results can even be obtained in some zero-dimensional models, which Anwar invented for Sharanya, and Anwar invented this and solved these, and you can see very similar behavior in these models, and you can explore a whole variety of such models. Let me go now to thinking a little more about this flux involving chi. Now, the flux involving this chi, this cross correlation between the velocity and the magnetic field, can really be sorted out only if you assume some closure. For example, if you assume the tau kind of closure, then in the simplest case, this cross correlation can be rewritten in terms of velocity correlations and magnetic field correlations. You can plug this in here. And of course, as Ethan already mentioned, if you have isotropic turbulence, you get zero flux. If your velocity and magnetic correlations have somehow come into equilibrium with each other, you get zero flux. But there is something which breaks this symmetry between velocity and magnetic field correlations, the anisotropic pieces, and that is shear. If you look at how shear acts on the velocity field, suddenly, sorry, I changed from V to U here, the velocity field and the magnetic field, then you will find that the shear acts as minus U dot grad U bar for the velocity field, but plus B dot grad U bar for the magnetic field. And this can actually break the symmetry between the velocity and magnetic field. So the non-linear back reaction of this flux is not really by these anisotropic pieces cancelling each other, but they could even add, and it's not yet complete. So for example, if you just took this piece and you calculate the flux due to Wozniak and Cho, then is there in an appendix in our paper by Axel and myself, then you get something of this thing which is more or less what Ethan kind of mentioned. There is something quadratic in B, something proportional to shear. He wrote it in a slightly different way. I write it this way because this tau is what is here, and this tau star is something which comes from here. Of course, there is one danger here, and I have slightly looked at other closures, and these other closures can even lead to an effective tau which is suppressed. So it is still, we are still not completely out of the woods. For example, if you do something which Part2 was doing in the Newton Institute meeting, then you can get in the nonlinear stage these effective correlation times, because these are not really correlation times, these are changes in the propagator due to renormalized propagator. That can get suppressed in some sense. So one still has to look at that. And what we found, Sharanya, Anwar and myself, in the simple zero-dimensional models, and which Sharanya has now verified in the 1D model, is that you need a finite amplitude kind of field to kick off the Wozniak-Cho flux. So this is what we found, and I won't go into the result. Let me just end by saying that to me, I am happy that at least I understand what is helicity density for the random field and what is helicity density flux for the field, although it is an intrinsically topological quantity. the advective flux may be actually essential, and I'm not convinced yet that all the other fluxes can arise without you kicking it in some way. And computing, of course, all these fluxes under turbulent EMF needs a closure or renormalization or something which we have to keep exploring. We know something about the tau closure, but we need to know other things. The VC flux can enhance the magnetic field, but needs a finite seed. You need to explore fluctuations in more detail, I think, and this is something which I think we should keep doing, and to some extent, Sharanya has started doing this. Need to compute the triple correlation flux. I mean, you have all these things, right? But there is something which is unknown, and if it is going to cancel your other stuff, you need to have a handle on that. And so lots to think about for the next few weeks. Thanks.
So if you have all these galaxies throwing out clouds of velocity, so what happens next to it? You have the clouds hanging around and up the galaxy have positive and